on Zoom. All right. While people are joining us on Zoom, let me start with the introduction as well as the news for the coming days at the center. Next week, it's Thanksgiving break here at the University of Pittsburgh, so we will not have any event at the center. Looking forward to a well-deserved break. And the following week, we'll be back for the last week of activities at the center. So we only have 2 weeks before the end of the term here. We have a talk by Lucy Mason, who is a postdoctoral fellow with David Wallace in the Department of History and Philosophy of Science here at Pitt. And she will be talking about methodological intersubjectivity. The talk is at Tuesday at noon. The talk is in person at the center, but as you know, we also are streaming all the talk on Zoom and on YouTube if you want to follow them. And the last talk of the semester will be given by Armin Schulz, also a former fellow who will be coming to Pitt to give his talk on the case for eliminative pluralism. And the talk is on Friday, the week after Thanksgiving at noon as well. The talk will be in person, but as usual, we'll be streaming it on Zoom and also on YouTube. And then it will be the winter break. So if you want to catch up the last talks at the center, you'll have 3 opportunities, including today's talk by Sam. All right, so it's my pleasure to introduce our speaker today, Samuel Schindler, who is a former fellow of the center. So that's part of the featured former fellows, where we're bringing online fellows who spend a semester or a year with us here at the center. So it was a wonderful opportunity to bring back members of the extended family, as one might say. And Sam is definitely one of them. So it was a pleasure to talk to Sam and see him. Sam is Associate Professor of Philosophy at the Center for Science Studies at Aarhus University in Denmark. He works on many different topics. His main focus for a very long time, including when he was at the center years ago, is in general philosophy of science, particularly the relation between evidence and theories. That work has led him to publish an influential and very positively received book, Theoretical Virtues in Science, Uncovering Reality Through Theory. But he has done work in other areas of both philosophy of science, but also philosophy more broadly. One of his research projects, started maybe a decade ago, was on intuition in philosophy and in science. That has led actually to numerous publications in studies, the Australian Journal for Philosophy, Philosophical Studies, so in top journals, looking at the place of intuitions, both in philosophy and in science. He has also done work in metaphilosophy, both in metaphilosophy of science and in metaphilosophy more broadly. I'll mention some of his work on case studies, for example, the role of case studies in philosophy of science. And he has actually recently published a few very interesting empirical work on how scientists think about various theoretical virtues. There's a paper out, or maybe coming out in studies on predictivism that actually uses methodology. So as you can see, a very large set of work using a very diverse set of methods in general philosophy of science and in philosophy more broadly. Today, it's our pleasure to welcome you back, Sam. So floor is yours, or I should say screen is yours. I'm going to disappear for a little while. And why don't you try to share your PowerPoint right now to see whether it works fine?
Yeah. Okay, sure.
Beautiful. All right, I can hear you. We can see you. So I'll be back live in person in 50 minutes. I'll be the background, but meanwhile. All right. Ciao, ciao.
Okay. Thanks very much for this really nice introduction. And my understanding is that many people in the room are fellows currently. And I can only say that when I visited 14 years ago, I had a tremendous time. I learned a lot. It was very stimulating. I met a lot of people that became friends. So I really look very fondly back to the time I had there, and I'm sure you'll have a similar experience. Okay, so yeah, this topic is a little bit of something new for me. I mean, I've worked on discovery before, and I'm trying to expand now into the realm of AI, maybe for obvious reasons. Okay, so I don't need to explain to you that there's been a lot of enthusiasm about AI in the general public, also concerns, of course. But this is pretty much reflected in science itself. So here you have a review article that appeared in Nature, where it's being said that AI is being increasingly integrated into scientific discovery, and insights that might not have been possible using traditional scientific methods alone become possible with AI. Here's a paper by the president of the Association for the Advancement of Artificial Intelligence, saying that AI may write scientific papers in the future. And then there's this oft-quoted paper that puts forth the Nobel Turing challenge, which says that, or which aims at developing AI scientists capable of autonomously carrying out research to make major scientific discoveries and win a Nobel Prize by 2050. So this is also by lights of the author a little bit tongue-in-cheek, but still there's a lot of confidence that AI will even develop autonomy to the extent that it can make discovery itself. Okay, so this just to illustrate some of the enthusiasm, but my focus is actually pretty narrow in this talk. I want to focus on AI-driven attempts to make new discoveries of new phenomena. And traditionally, philosophers, when they think about discovery, they usually think of discovery of ideas. This has very much to do with the traditional two-context distinction between the context of justification on the one hand and the context of discovery on the other hand, and the latter being the question: how do scientists come up with theories, hypotheses, ideas, and is there logic to it? And there was a big discussion about that in the 60s to the 80s, 1980s. Maybe not so prominent anymore, this discussion, but the context distinction you do find. And in the SAP article on discovery is actually all about discovery of ideas. But this is something that I'm not concerned with here. So there's a nice contribution that links up to this by Eamon Duade. I'm not sure it's the right pronunciation. But he basically argues that AI can be super useful in making scientific discoveries understood as ideas, new scientific ideas. So the view that I want to defend here is that with regards to the discovery of new phenomena, there are limits to how much AI can help us do that. Okay. Here's the agenda for this talk. First of all, I'm going to do some stage setting, and I'm fully aware that many of you will have some sense, at least some sense of this already, but I just want to make sure we have a common ground. And I'm going to present what I call the dilemma for DNN discovery. So DNN stands for deep neural learning. I'll talk about that in a moment. And I'm going to talk about then a little bit about what I mean by the discovery of new phenomena, and what the value of that might be for science, why we should care about it. But that may also be obvious to a large extent. And I'm going to spend the rest of the talk going through the dilemma and justifying arguing for the first horn of the dilemma. So one expression that I have here that describes this first horn is that DNNs are epistemically narrow, and in the second horn I argue that DNNs are causally blind, and both of these things, or both of these horns, leads to this more skeptical conclusion about the possibility of DNN discovery of new phenomena. Okay, so neural networks consist of layers of nodes and edges. So these networks are loosely modeled on the brain. In the brain, you have neurons and synaptic connection between them. And the edges in these networks, they weigh the signal coming in from one node to the next. And the nodes then compute an output by means of a nonlinear activation function. And during training of these networks, the weights or the edges change. These networks are themselves models, so they don't physically exist. That's something that inspires the writing of computer code. Okay. So what is deep learning? Deep learning basically refers to the fact that, or deep learning, what you require is a number of hidden layers between the input layer and the output layer. And that's a crucial bit, because in comparison to earlier neural networks, so they've been around for quite a while, since the 1980s at least. I think it goes even back further, 60s maybe. In comparison to that time, the current computing power allows us to have many more of these hidden layers than before. And that results in much more complexity. So ChatGPT, for example, has 175 billion parameters in the third version, and was trained on 300 billion text tokens. And the current model even has 2 trillion parameters apparently, and is trained on 13 trillion tokens. So insane amount of data that is being used here, and parameters to train these models. One class of training is supervised learning, I would say the main class. What you do in training these networks is you have a training data set, and you label the things that you want the network to pick out. So for example, images of cats, and you train the networks to recognize cats and distinguish them from dogs, for example. So that's called labeling. It's a bit of a technical term. Basically means that you ask the network to associate a certain input and a certain output. And there's also self-supervised learning, which has played a major role in recent developments. And I consider it to be a variation of supervised learning. For example, the large language model designed by Google, for example, masks part of the input that it's getting, and then tries to predict the masked part of the input. So say since the cat is on a map, and then it would mask some of that, some of these words, and then try to predict them. So yeah, it can be automated. This process of supervision doesn't need to have explicit human input. Okay, and in the supervised learning, you have a loss function that measures how far of the output of the network is from the target. So target in this case would be cat. Then if there's no match between the target, or if there's not a good match between the target and the output, you have this loss measured by loss function, and that loss is being propagated back through the network with this algorithm called backpropagation, which then determines the gradients for each weight, meaning that it checks basically the sensitivity of the loss on the specific weight. So how much would the loss change, if I were to change the weight of one of these nodes, or one of these edges. And then there's an optimization algorithm, a gradient descent, that adjusts the weights to minimize the loss. So that's the very rough explanation of supervised learning. And then there's unsupervised learning, which proceeds basically without feedback on its outputs, and then it's used to find patterns in the data. One very well-known algorithm is k-means, which looks for clusters in the data by trying to minimize the squared distance between data points and centers of clusters. But this is not a DNN, and we will later today talk about or consider an example of unsupervised learning using DNNs, but that's rather unusual. most DNNs work on the principle of supervised learning. Okay, so with the stage setting, I want to introduce this dilemma that I've come up with. And the first one is either we use supervised learning, but then by the very design of such learning, we cannot discover phenomena that differ significantly from the target. And the second one is, we use unsupervised learning, but then by the very design of DNNs, we face what I call the aggravated artifact problem, which is that it's especially hard to discriminate a real effect from an artifact when one uses DNNs. But that, of course, is a precondition for the discovery of new phenomena. Okay. So I want to say a little bit now about the discovery of new phenomena. It's quite obvious that the more we learn about the world, the better it is for the progress of science. So that's trivial. But then we do more than that when we discover new things. New discoveries can also force us to revise our preconceptions and to think anew. And this basic point was made, I think, maybe most forcefully by Thomas Kuhn, of course, in The Structure of Scientific Evolutions. He talks about the discovery of oxygen and the overthrow of the phlogiston theory, which then triggered this overthrow of the phlogiston theory. And there's this essential tension, of course, that Kuhn points to as well. So normal science normally is quite conservative, and it gives scientists strong guidance for what to look for. But it also allows for unexpected results, right? So there's this tension between conservation in a sense and the allowance for radically new things to be discovered. Okay, Kuhn also talks about the discovery of X-rays in this context. And Röntgen's original plan was to study cathode rays during darkness, because at the time there was no clear conception of what cathode rays were. So they are just basically electron beams. So he covered the tube in cardboard, and he wanted to just study the effects of those beams. He thought of them, I think, as some form of light, as many people as well during the time. But then he noticed entirely unexpectedly that the fluorescent screen standing in the vicinity of the tube lit up when the tube discharged, and then this detection of this anomaly was followed by a phase of exploration and reconceptualization. What are the properties of the anomaly? What is it caused by? How can we make sense of it theoretically? So, for example, he found that X-rays penetrate various materials. He realized he could not refract and focus X-rays with ordinary lenses, which is weird, a weird thing to do retrospectively. But again, he thought of them as a form of light. And then he also took the first X-ray photograph of his wife's hand, who reportedly said, "I have seen my death after viewing this picture." Okay. So this is, of course, well known, but what I want to emphasize here is that science is able to detect and explore novel phenomena, and for that, instruments that have been used in science, like the cathode ray tube, must be epistemically open. By that I mean the instruments must not preclude the observation of effects that have previously been not been expected. It must allow for surprises, serendipity, like in the case of X-rays and in the case of oxygen. And I want to argue in this talk that DNNs are not like that. They are not epistemically open. They're actually, to the contrary, they're epistemically narrow, and that makes them unsuitable for the discovery of new phenomena by design. Now, I want to turn to AlphaFold. AlphaFold was designed by Google, and it solved the 50-year-old protein folding problem. So it predicts protein structures from amino acid sequences, and this is quite enormous. So this was a well-known problem in the field, and there were solutions, methods that were proposed that were not nearly as effective as AlphaFold's algorithm. It also resulted in a Nobel Prize last year in chemistry. So surely a tremendous success. And a big part of the success is based on supervised learning. So the AlphaFold was trained on known sequence libraries and known protein structures. So was trained to predict these known structures from known sequences. But it does it in a tremendously effective way. So you can now predict unknown protein structures, and this is all amazing. So I don't want to downplay any of that, but at the same time, it does not predict anything that is not trained for. AlphaFold, right? It's trained to predict protein structures, and of course that was the purpose of it. So there's nothing wrong about that. But by its design, it could have not predicted something else, maybe peptides, for example, right? That would have been extremely strange and odd if that would have been possible. I'm not, yeah. So I think that's really questionable whether it would have been. Now, sorry, I want to illustrate that with a little thought experiment. So imagine you had some binoculars that work just like supervised and DNNs. And now you're going on a safari and you want to observe zebras. Sorry, I have to drink a bit of water. You want to observe zebras on that safari. But to do that with your strange binoculars, you have to train your binoculars on thousands of zebras before you can see anything. And anything that shows up in your glasses and isn't a zebra, you will just ignore. You will not even take notice of it. It will just be blurry. But once you've done this training, you have extremely good binoculars. You have very sharp view of the zebras. You can see them super far away. You see more than anybody else, and so on. But of course, now that you have these fantastic binoculars, you can't see anything else. So if you want to see a lion, you have to go through the same process again. And now, suppose you want to discover animals you haven't seen before and you have no knowledge of, say the aardvark. So how would you go about that then with these strange binoculars? Well, without fixing on the animal, you cannot really train the binoculars on them. But in order to fixate the binoculars on them, you have to have the sense that there's an animal in the first place and interesting one to look at. And it's not quite clear how you can do that. Similarly, with supervised DNAs, we need to know the target already for them to discern the target, basically. So AlphaFold is super good at discerning and predicting protein structures, but nothing else. Okay, and in that sense, I want to say that they're epistemically narrow DNAs. Now, there's an interesting case that I want to talk about a little bit that you may think contradicts a little bit of what I'm saying. So halcine is a new type of antibiotic that was discovered with the help of AI. That's how they did it. They trained the DNA to predict growth inhibition of E. coli using a collection of a couple of thousand molecules. And then they applied the DNA to a massive known compound library with about 100 million molecules. And halcine had been known since 2009, but was categorized as a J&K inhibitor for possible treatment of diabetes and metabolic disease. Fun fact, it was renamed halcine because they used AI to make this discovery after the famous Kubrick film, Space Odyssey. Halcine is currently being tested. It's still open whether the drug will be, or sorry, the antibiotic will be really effective, or whether it can be used in humans and so on. But it seems promising, and furthermore, it's also quite different from previously known antibiotics, both in terms of structure and effectiveness. So usually antibiotics target bacterial cell wall synthesis and protein synthesis. But halcine instead disrupts the bacteria's ability to maintain an electrochemical gradient across its membrane. So the discovery of halcine seems to be both new and surprising, right? It has these features that we haven't seen before, and that could be great as well in terms of antibiotic resistancy. So you have a new antibiotic that you can use as an alternative, and that has a completely different effect, or different mechanism. Yes, and that seems to be quite contrary to what I've claimed. So how do I make sense of a case like that? So I do think again that this is fantastic. So I don't want to downplay it in any way. If this really pans out as a functional antibiotic, and it really proves, I think, how big an impact AI can have on science and how it can help us to make progress. But at the same time, again, the DNA was trained to look for antibiotics, right? So we knew what we were looking for, namely antibiotics, and the molecule itself was already known. It was obviously mislabeled, or people thought of using it for different purposes. But it's not a new object that we discover or a new phenomenon in the strongest sense. And at this point, you may be saying, Sam, you're really being unfair here. This is perfectly fine as a discovery of a new and surprising thing. But scientists themselves are actually looking for more novelty than what's embodied in halcine. And that's where we turn to physics. And the standard model in physics describes our current physics quite well. But there are several problems with the standard model, and physicists are looking for physics beyond the standard model. It's actually abbreviated BSM physics. So again, the standard model has predicted, for example, the Higgs boson successfully, and that actually was reason for some disappointment, because physicists were hoping to we had a lot of hope that supersymmetry theories might be theories that would replace or supersede the standard model, but the discovery of the Higgs boson is really undermined these efforts. But yeah, again, physicists are very confident that the standard model is not God's last word. In a sense, there are many problems. So, for example, gravity is not included in the standard model, so only the other three fundamental forces. Neutrino mass has been discovered is not accommodated by the model. There's a lot of pre-parameters, and physicists would like a theory that really lets us derive these parameters and not having them to set them by hand, as it were. Dark matter is not part of the standard model, and there are many other issues. So so what do physicists do? Well, they're holding out for some lead to develop the current physics further by trying to make new discoveries, something unexpected that can't be accommodated by the current model, that could help them make theoretical progress. Okay, I'll get back to this later in the talk, but I want to introduce the second horn of the dilemma before I do that. So again, the second horn is when we use unsupervised learning, we face the so-called aggravated artifact problem. Again, it's especially hard to distinguish or discriminate real effects from artifacts. And this has to do with much discussed opacity of DNNs. The reason why this is so difficult. And even though there's a lot of work on ethics of AI and opacity of AI, there's maybe not so much on the epistemology, but what philosophers have done is bringing some nuance into thinking about opacity. So, for example, Catherine Creel, in a much cited article, she distinguishes between functional, structural, and run transparency. So really, between fathomability, intelligibility, tractability, in Surgard, and paper in the Canadian Journal of Philosophy, Between Inference and Training Capacity. So I don't want to go into too much detail with these distinctions, and there's some differences as well, some disagreements, but a common denominator for all of these works is that is an appreciation that the complexity of DNNs is really the decisive factor for the opacity. At the same time, there's a sense in which DNNs are really fully transparent. Operationally, we know exactly how they're working. We know exactly what the algorithms are that are being used in these works. So I think I take this to be the most important message that you can extract from any discussion so far about opacity. And yeah, obviously, if we didn't have this understanding, we couldn't build DNNs, right? So we have that understanding, but still, because of that enormous complexity, we have this opaqueness. Okay, and opaqueness has been argued need not be problematic per se. So there's this influential paper by Emily Sullivan, who argues that there's what is really important. What really matters is that there's a link uncertainty here between the model and the world, and we need for us to be convinced of the mechanisms that the model outlines for us, or maybe the relationships that the DNN identifies. We need some evidential support for that, and she compares that to the Schelling model, which proposes a mechanism for racial segregation, and she argues it's just like that in DNNs. So once we have this evidential support, then there's no problem really. And Duade, this paper that I mentioned before, again, he argues that the discovery of new ideas is perfectly sound with opaque DNNs, even though the justification of ideas is not. But so these are nice contributions, but what I want to argue is really that the opacity is indeed problematic when DNNs are used for the purpose of scientific discovery of new phenomena. Okay, so here I want to make two claims. And the first one, understanding of instrumental artifacts requires some level of transparency. That's a little bit of a vague, but hopefully we'll get clear in a moment what I mean by that. And I'll also argue that DNNs are causally blind. They pick out features that are causally irrelevant to their targets, and that's also a problem when it comes to discovery. Okay, so classical instruments, to start from there, are fully transparent. So for example, the light microscope, right? We know all the physical processes that occur in the microscope for us to see images. And because of that, because we have that transparency, we also know the sources of error. So there's several aberrations, for example, chromatic and spherical aberrations. So a light of different wavelength is refracted in different ways, so that you get a different focus. And similarly for spherical aberrations, sorry. And because we know these principles, we can correct for these errors and these error sources, right? And here you might say, yeah, true. But we also have transparency for DNNs, as in the way that I outlined before. We know exactly how DNNs adjust the parameters, how they calculate the activation functions, loss function, and so on. But the difference is that this understanding does not translate into a good grasp of potential errors, in contrast to traditional instruments. So there are no specific parameters that you can tweak or fix in order to prevent errors from happening, quite in contrast to traditional instruments, and that's a problem. So here, one may think of explainable AI. So those of you who know a little bit about this field, explainable AI tries to develop algorithms that make DNNs more intelligible to humans. That's why it's called explainable AI. And the different methods. Some use visualization, some use saliency maps for images that influence the predictions that the DNN is making. However, most of these methods are post hoc. So you have DNA that is trained on data, makes its predictions, and then you apply the algorithm to see what may have influenced the decision. And also local, so the XAI gives you some insight into a specific prediction that is being made, but you can't get a kind of holistic understanding of the underlying dynamics in this way. Okay, and there are some broader critiques of the prospects of explainable AI. So it has been argued in these famous papers here, or influential papers, XAI is misleading, potentially wrong. It doesn't tell you how the DNN actually makes its decisions. It only gives you a human-friendly model of these decisions. So it's a very simplified way of looking at the way that the DNN is working. And XAI can also be quite uninformative. So it only tells you what features the DNN is, in a sense, looking at when making its predictions, but it doesn't tell you why it does so, and it doesn't tell you what the DNN is doing with this information. And Rudin gives this example that I have here as well. So this is a DNN looking at a husky, and the first picture, the picture in the middle gives you a saliency map of where the DNN, quote unquote, is looking at when making its decision. And in the third picture, so the picture to the right, the decision is flute. So in this picture, the DNN is categorizing the picture as a flute, so an instrument, which is super strange, right? And Rudin argues you can't see any from these pictures, from these salience maps, you really can't tell why the DNN is coming to these weird decisions. Of course, that's an extreme example, and XAI has been useful in many contexts. But yeah, there are also problems. Yeah. Yeah. So this other feature I want to argue for that we have in DNNs that's problematic is what I call causal blindness. And to be more precise, I should say also constitutive blindness, but I just call it causal blindness for simplicity's sake. So what I mean by that is that the DNN is prone to picking out features of in the data that are causally or constitutively irrelevant to the target. And this has been a tremendous problem of DNNs in many contexts, and has been described in different incarnations. For example, bias. So it's well known that DNNs replicate racial biases, for example, adversarials. So you can add data to a data set that's almost imperceptible to humans, and that can make a difference to the way that the data are being categorized. Clever Hans problem discussed by Boge recently, in and out of distribution performance and shortcut learning. And I'm going to say a little bit about the last couple in a moment. But yeah, this causal blindness of DNNs leads to what I call the aggravated artifact problem. Okay, so here's an example of shortcut learning. So you have this training set in the top. There's stars and moons, and you have to. And the task is to associate the stars with A's and or categorize them as A's and the B's and the moons as B's. On the left-hand side, in the second row, you see on the left-hand side a human categorizing, and on the right-hand side the machine or the network, and the categorization is the same, right? And the goal is, right, to of course make this categorization on the basis of the shape of the object. But what the network is actually doing, it's looking at the location of the objects, and if you change the location of the objects, then you get a different result. Then you get a wrong result for the machine, and that's also known as in and out of distribution problem, right? Because you train the model on a set of data that has certain features, and then once you make the step out in the wild, then the model fails. Okay. There are more examples. Wolves on snowy background versus huskies. So the model learns to associate or to make the right decision on the basis of the background rather than on the basis of the actual animal. Pneumonia detection. It has been found that the DNNs have been very effective in doing that, but then it turned out that they based the success on metal tokens being placed on the patient by the radiologist. Skin cancer recognition was actually based on the markings, the skin markings that you do for surgery. And obviously, all these features are either constitutively or causally irrelevant to the target, and in the latter case, would be skin cancer, right? And if you were to build a machine or an instrument, you would never think of using any of these features to make your decisions, right? Or to make a discovery. So that tells you that these features are really completely causally and constitutively irrelevant. Okay. Again, this causal blind is particularly a problem when we look at new phenomena or trying to discover new phenomena, because then we need to distinguish real effect from artifact. And generally speaking, when we make inferences from the data to the phenomenon, then we better make sure that we're basing our inferences not on artifacts, but rather on real features in the data. And likewise, when DNNs are making predictions, they better be based on causally relevant features rather than irrelevant features, so that we can trust the predictions in case we don't know what the target is, right? But because DNNs are opaque, artifact discrimination is particularly difficult and problematic. We may not know which features in the data underlie the predictions. Okay, so the rest of the talk I want to turn back again to physics. So how are physicists approaching this issue of finding physics beyond the standard model? Well, one way is to actually use DNNs to try to discover new physics. And one prominent method here is our so-called autoencoders. So autoencoders, they consist of an encoder and a decoder. So that's a neural net with a bottleneck, so fewer layers with with a smaller width. So what you get is a compression of the data coming from the encoder to the bottleneck, which is also called latent space, and then this is being decoded in the last part of the autoencoder. And then there's a loss function, reconstruction error, more appropriately. So the autoencoder must try to minimize the difference between the input and the reconstructed data, or the other way around, rather. And what's the point of this? Well, with this compression, you make sure to only capture the most relevant features of your input, and that's very handy, right? If you're looking for new physics, you're not interested in the noise and the data and so on, so you can get rid of those by using autoencoders. Okay, just want to illustrate this with an example from brain science, where they're also being used autoencoders, so not just physics. So you can train autoencoders on healthy brains, and then the autoencoder tries to minimize the reconstruction error, and then when you apply it, the autoencoder on damaged brains, is the lower part of the image, then the autoencoder fails to reconstruct the image, right? It is because it's been trained on normal brains, so it fails to reconstruct the signal, and then gives you this residual signal in the end, which is the difference to the normal signal. Okay, and that's how, in principle, how it works in physics as well. So in the second step, when you get a reconstruction error, you're hoping that this is indication of finding new physics, right? Because it diverges from the normal background, as they call it. Okay, so back to physics. Interesting fact that physicists actually using simulated physics, so computer-generated events, to train the autoencoders. And why is that? Well, so one important important reason is that so first of all, it also gets rid of noise that you don't need, and features in the data that you don't want to capture. But also, you also want to make sure that you don't train your autoencoder on the physics that you're trying to discover, right? So you have a bunch of data coming out from the Large Hadron Collider and so on, and it's possible that the new physics is somehow hidden in there, right? If you train the autoencoder on that background, then you can't discover it. So that's maybe the more important reason why they use simulated physics. And then they train them on the known physics. They use these quantum chromodynamics jets, which you can see on the top. And then in order to validate the autoencoder, they deploy them on jets from top quarks, which you can see in the lower. So that's the lower figure. And why are they doing that? Well, because these top quarks or top jets, they have a distinctive topology. So they're quite rare, and you can see from the pictures already that they're more complex. So the T jets they have 3 prongs instead of 1. And the idea is that if there's something new, then it should stick out in the way that these T jets stick out from the data. Okay, so a couple of interesting issues that I want to highlight. So the first one here, again, I think that's evidence for autoencoders, like all DNNs, being causally blind, and that causing issues. So Finke and colleagues discovered something interesting, and that's been picked up by Florian Boge, a philosopher, and Direct, in the forthcoming chapter in the book on understanding. But yeah, the physicists found that when they trained the autoencoders on the data or in the background, they noticed that the autoencoder focuses or fixates on the brightest pixel in the images that it's being trained on, and it ignores the dimmer pixels. So here on the top you have an image of a QCD jet, so that's the background on the left, and on the right you have a top jet. You can see already the red part indicates a bit more structure than on the left, the picture on the left. And this is not just one jet. These are average of 40,000 jets. So that's what the DNNs are being trained on. This resulted in a reconstruction failure and therefore a detection signal for the more complex images containing dimmer pixel, right? Because they diverge from the normal. The normal is the QCD jet on the left. That's what they're trained on, and then they're being applied to these more complex jets, the T jets, and then you get this reconstruction error, just how it's supposed to be. But then the problem is obviously that pixel brightness is completely causally irrelevant to whether there's new physics or not, right? So there's a clear case of shortcut learning, so that the model learns to recognize a pattern in the way that's conducive to the goals that it's being given, but then it does it in a way that's completely misguided. Just for interest, how did they find out? They reversed the autoencoder. So they trained the autoencoder on the top jets first, and then had it reconstruct the QCD jets, so the other way around. The interesting thing was, or the weird thing, was that the QCD jets were reconstructed better than the top jets, even though the network was not trained on them, which was super strange. And the reason for that was that again, the autoencoder focused on the brightest features on the top jets, and therefore it kind of implicitly learned also to recognize the QCD jets. Okay. So that's the first issue. Another problem with regards to the causal blindness of autoencoders is that autoencoders automatically learn jet mass from the basic kinematics of jets. For example, the momenta of the constituents. These jets with a heavier mass on top of that, they are harder to reconstruct than the jets with one prong, and that leads then to heavier mass, or jets with a heavier mass being automatically classified as an anomaly. So in other words, there's a correlation here between mass and complexity. And instead of detecting different structures as autoencoders are supposed to, they detect jets with more mass. But of course, there's no reason to assume that physics beyond the standard model has got to be more massive. Okay. So here's the final point that I want to make, and that's a more general issue. So autoencoders must strike a fine balance between encoding the data and reconstructing them. So on the one hand, they must have a high reconstruction fidelity, so as to successfully reconstruct the background data, right? So they have to reconstruct the background data well for this to work, for autoencoders to work. On the other hand, the fidelity cannot be too high because otherwise they will reconstruct only the known physics and ignore potentially new physics. And this is what they found. Fraser and colleagues in this article, they found a trade-off between background validation and anomaly detection efficiency. So they tested 3 model networks with varying depth, and the deeper the network, the higher the compression. So on the left-hand side, you see this QCD validation. So that's the background physics, and the curve that is blue stands for, or represents a shallower network, and that turned out to be better at reconstructing the background, but worse at detecting a signal. So the lower the curve here, the better the reconstruction. That's good for the background physics, right? But the other pictures or the other diagrams here are for the top jet and the W jet. So these are the pseudo signals. So they stand in for a new physics, or example for used to train used to validate the autoencoder. And there you can see that. So there again, the blue curve is the lowest curve, meaning the reconstruction is the best. But it should be worse, right? For you to detect the signal, you have to get a high reconstruction error. And they found the reverse for deeper networks, which you see in orange and green. It's just the other way around, right? So you have this trade-off between a good reconstruction of the background and a good performance in detecting something new. So the problem is that, and that's crucial, if you do not know the signal, if you do not know what you're looking for, you cannot make a good decision, right? If you knew what you were looking for, if you knew that the new physics is just like the top jet, then you just choose the model that is performing well in the middle diagram. But it could also be that the new physics behaves more like QED, the QED background, which is on the left-hand side. So without knowing the signal, you cannot make a good decision which one to choose, and you can't have a good performance on both of these parameters. Okay. So this is how Fraser and colleagues conclude their discussion, and this was very nice for me to see. So they say this is the challenge of signal-independent searches for physics beyond the standard model without a signal model in mind, namely target optimizing analysis strategies is hard to do in a principled manner, what we just talked about. And in fact, they also express general doubt about unsupervised searches and conclude that autoencoders by their very design may not be suited at all for finding new physics. So they write, one has reason to be suspicious. Machine learning methods work great at optimizing a given loss, which is meant to correlate strongly with the problem one is trying to solve, so the target basically. For autoencoder anomaly detection and optimization, background only is not aligned with the ultimate problem of interest, namely finding the physics. So it should not be surprising if the autoencoder does poorly. So this was nice for me to see, because really it's just another way of putting this, the first horn of my dilemma. Okay. Of course, other physicists may not be as pessimistic as Fraser and colleagues, and it's still an active research area, and it may also be premature to draw any strong conclusions here. But even if physicists would overcome these difficulties, and if there was a solution, again, these problems seem to be quite principled and quite general, so it's not quite clear how that could work. But even if we grant that, it's even hard to see how that could be extrapolated to other sciences, right? Because physics, after all, is a highly theory-driven enterprise and makes very precise theoretical predictions, which we saw came in very handy in training the autoencoder on this simulated physics. And we don't have that advantage in the other sciences. So if anything, it's going to be only more difficult rather than less in other fields than physics. Okay. So this is my conclusion. I have argued that DNN-driven search for new phenomena faces a dilemma. Either new discoveries are precluded by the very design of supervised DNNs, or the discovery of new phenomena is made exceedingly difficult by the aggravated artifact problem. And here the issue is that DNNs are causally blind. They cannot distinguish causally relevant features. And yeah, my arguments, I think, should raise some doubts about the discovery of new phenomena with DNNs. And particularly, I think the architectures of DNNs sets limits on their use in science. Again, causal blindness, but also epistemic narrowness. But I should emphasize that in no way do I think that this undermines the general usefulness of AI in science. So I think still a lot of progress can be made apart from the discovery of new phenomena. Okay, that's my talk. Thank you very much.
Thanks, Sam. Great talk. We have plenty of time for questions. So let me tell you how the Q&A will be working. If you go to the bottom of your screen, you see a box with Q&A on it. And you can write your name there. And if you write your name there, I'll be able to promote you to participants. And you can ask a question directly to Sam. So if you have a question, please go to the bottom of your screen now, write your name in the Q&A box. I will promote you to participants and you'll be able to ask your question. If you're at the center right now in the main room, please do the same as well and turn the camera on so that we can see you for the Q&A. All right. We already have someone. Let me promote you to participant, Camilla. Can you get us out of the slides?
Oh,
Sam?
sorry.
Yeah.
Sorry.
All right. Thank you very much. Camilla, floor is yours.
Okay. Can you hear me?
Yeah, but we can't see you, but we can hear you. It's fine. Yeah.
Okay. My hair is horrible, so I'm not gonna give you any video if that's okay. So, thanks for the call, for the talk. I'm glad that more people are interested in this topic, in the impact of AI on science. So I wanted to know your thoughts on a couple of points that I think didn't receive enough attention in the talk. So we talked about supervised learning and unsupervised learning, but so we have a very important third type of learning, which is called reinforcement learning, and like AlphaZero, AlphaGo, all of them were based on that, and today LLMs are relying on those heavily. AlphaGo, for example, had this novel moves 37, which many people considered a very, very new move in Go, and that was basically a result of this reinforcement learning. Also, self-supervised learning, you basically somehow put that under supervised learning, but I I personally think that that deserves its own treatment because supervised learning usually involves people actually labeling stuff. So very, very explicit like knowledge involvement. While self-supervised learning, you can basically dump a lot of data there and like pictures, videos, anything. And the system can just omit part of it and try to guess what that part should be. And from that, it learns to do better next time. And many people might say that's a way that to learn and generalize very well without giving it any explicit guidelines. Thank you.
Yeah, that's a very, very good question. In the previous iteration of this talk, I had another distinction between target and target specific and target unspecific learning. Which I thought maybe would have complicated the talk a little bit, but too much. But that's kind of my view about these other types of learning, that they fall under these broader labels. And so self-supervised learning, so I mentioned it, right, that they're being used in these large language models to great effect. So first of all, also there, you usually have a blend of methods. So it's not as simple maybe as saying, this algorithm just uses that type of learning. There's usually a blend, but for example, for AlphaFold, that just played a large role, supervised learning. And even in language models, large language models, you have some stage where you have supervised learning. But then what you do in self-supervised learning, so the different varieties. I mentioned BERT, where the program masks part of the input and then tries to predict the rest. But I consider it to be part, or an instance of target specific learning. So that's the distinction I made earlier that I alluded to. Why is that? Well, imagine you would train your language model on randomly structured or randomly random sentences, in the sense of the words are just randomly presented, right? Then the model wouldn't learn anything. So you have to assume that the input has some sort of correctness. It's the target you're aiming for, certain sentence structure, and so on. And of course, it's a little bit hard to maybe think of a correct target here, because obviously not any one sentence will be correct, but there's something like a statistical average over all sentences that you put into the language model that it will then aim for. I only spoke about supervised learning, but I consider it to be part of that broader label, maybe target-specific learning, and I think self-supervised learning is another instance of that. And then you mentioned reinforcement learning again. That's also used in AlphaFold to some extent. Again, there's usually a blend of methods, but also here I would say that you have a certain target, right? When you train a network, the target is just more abstract than reinforcement learning. So your target would be, for AlphaGo, learn to win a game, to win this game, right? And it doesn't matter what the specific moves are, but the goal is to win the game with the rules that need to be abided by. So you're absolutely right to point out that there are these other training methods, and they're important. And this was a bit simplified, I have to admit, here for the purposes of the talk. But the more extended version would include this broader distinction, and of course also a discussion of these other methods. I think that is two broad classes.
All right, thank you very much, Sam. Mark, do you want to join here? Yes, at the center. Mark, didn't you have a question? Oh, I think because the sound is not on. Mark, do you have a question, Mark?
Can you hear me now?
Yes, we can hear you. You can come closer to the screen if you want.
All right, I'll walk up there. Thanks, that was super interesting. I want to have you talk a little more about the transparency thesis. That is the idea that classical instruments are transparent. That doesn't seem right to me because things like the telescope, for instance, not understood at their time, and instruments have a way of going, through different theoretical changes. So it doesn't seem to be a big issue that we don't know exactly how. It's easy enough for the reasons you pointed out to see the limitations of an instrument and where its artifacts come from, even if it is a black box.
Yeah, that's a nice point as well. So you may remember that I put on the slides that I said you need some level of transparency. That's of course very unsatisfying in a way, but I agree that you don't need 100% transparency in instruments. But the difference is, right, that even if you don't know the exact principle, so there's of course different steps. So maybe you have some grasp of what your instrument is doing. I think that's the case of Galileo's use of the telescope. He didn't have a theory of refraction, but he knew roughly what was going on, light being refracted, and the parameters that were involved. You don't have that type of, or that kind of transparency in neural nets, I would say, or would argue. More importantly, even is that you don't have this translation. I mean, you don't have this translation to control errors in the way that you have with instruments, right? Even if you don't have the absolutely true theory of I don't know, say electrons in the electron microscope, right? You still have enough knowledge to understand what the error sources are, and you don't have that with neural networks. It's completely open before you train your network what kind of features the network will latch onto. Yeah.
Thanks. Next will be David.
Hi, Sam. Great. Thanks for that talk. So I was relatively unmoved by the considerations that you proposed. So you could have, for example, semi-supervised neural networks. I know you mentioned that there are, of course, other classes of neural networks. You think they're subject to the same sort of limitations. With semi-supervised, you can sort of detect structure that doesn't match what's in the labeled subset. And then so you can kind of imagine the network sort of saying, okay, there's something going on here. So it seems like they could discover sort of unexplained or unlabeled structure or something along those lines. And then, of course, you would need to confirm it. And I don't see how this is any different from discovery that a human might go through when they're using a new tool or not, where you uncover some sort of novel structure. It might be an artifact, it might not. Sometimes it's a complicated scientific process to rule in or out a potential new discovery, as many famous episodes in the history of science reveal. So I just, and even for example, in the antibiotic case, you said it discovered a new antibiotic. It didn't really discover a new antibiotic. What it did is it pointed this molecule, and it required all kinds of follow-up experimentation in order to confirm that there is antibiotic action, for example. At least I don't know the case, but that's what it seemed like. So it seemed like maybe, really it's to put the pressure in a relatively simple way. Couldn't it be that DNNs can discover new phenomena, but confirming the discovery maybe is a more drawn out process that requires some sort of conversation between scientists and potentially deep neural networks? And then, of course, you could just have the deep neural networks conversing between themselves in this way to do that kind of follow-up confirmation. So what would you say about that?
Thanks for the next question. Yeah. I mean, detecting an anomaly, right? That's only the first step. I totally agree with that in the discovery of a new phenomenon. And I mean, that was the case in the discovery of X-rays that I mentioned as well, right? You have this phase of exploration and trying to figure out what you actually discovered. So that's, I totally agree with. The question is, I mean, the question is about the first step, right? Can we expect DNNs to detect anomalies in a sense? Well, I think we just have to kind of throw up our hands, right, and say, yeah, maybe. But there's still this issue of that the the DNN may make its predictions on the basis of features that are completely, irrelevant to any kind of physical target that we may hope to discover. I don't quite see a way around that issue. But I think the best example we have for these attempts are in physics, and as I just mentioned, you seem to have some very principled problems that seem to make this just unlikely. But again, of course, the second one of the dilemma says is right. It's exceedingly difficult to make this distinction. Maybe it's not impossible. But yeah, as things stand, I would draw that conclusion.
Thanks, Sam. Louis, floor is yours.
Yes. Hi. Sorry, I can't show my picture.
That's
but
fine. Good to see you or hear you at least.
Pareillement. Thank you for the talk. It's very interesting. I think it. I see a lot of echoes of that among computer scientists. Although I haven't been following up like in the last few years as much as maybe I could have. But I see a lot of people trying to overcome those challenges with new architectures. Often it involves like, either agentic AI is sometimes seen as something like that. Like you try to have several networks that are sort of bouncing with each other to try to solve some challenge or find something. Or Benjo's brother has been working on something where he's trying to get transformers to to write code in order to introduce some maybe more logical thing in it, because back in the days these rule-based machines were actually pretty good at finding new information. I was wondering if this is something that you had thought about, or and if you think that's an interesting avenue to tackle those two problems.
Yeah, so I'm not quite sure what you're pointing to, but yeah, obviously there are different techniques and methods being used. For example, autoencoders, what they're trying to do is, so they call them variational autoencoders. They try to impose some order on the latent space, and by implying a Gaussian distribution. But yeah, so there are these complications. There are also, as you say, there are adversarial networks that try to, where they try to, get rid of adversarials for these networks. But yeah, so these are complications. But I'm not sure that they undermine some of, or that they would be able to overcome some of these other issues. For example, the mass correlation, right? So you don't put in the mass information at all, and the network discovers it, and then on the basis of that makes its anomaly decisions. That seems to be very hard to overcome. There's this trade-off between validation and detection. These seem to be principal problems, and I'm not sure. I'm not aware of anything that could overcome this, but yeah, of course, this may be also limited knowledge, and of course, who knows what physicists will come up with in the future. But even as I mentioned, right, even if that's the case, even if physicists manage somehow, then we still have there's still some room for skepticism, I think, about other science, because physics is so theory driven, and I can use these predictions to use networks to discover something new.
Thank you.
My computer froze for a minute, so good, I'm back now. Karim, floor is yours.
Thanks, Sam. That was really interesting. So in some ways, my big question was, is the dialectic you've set up such that by ruling out sort of AI generated scientific discoveries, you haven't sort of thrown out the baby with the bathwater in terms of paradigmatic human discoveries of novel phenomena? And I think that David did a really nice job of sort of addressing a lot of, or raising a lot of my concerns about the second horn of your dilemma involving causal blindness. So I want to turn to the first one about epistemic narrowness. So when you're talking about AlphaFold, one thing you said is they're like, well, it's discovering new protein structures, but you know, it's sort of designed to discover protein structures. And I thought to myself, well, can't new protein structures be novel phenomena to some extent? And I was thinking of sort of examples of this that might pose problems. Like you could use Röntgen, just if you want a very toyish example. Like he was looking for cathode rays and he found X-rays, so he's still looking for rays, but like we don't consider that to be a damning indictment on that as a scientific discovery. Or looking, for example, at like finding elements. I mean, the whole discovery of new elements, which you've written about, seems to involve actually quite structured kinds of discoveries where everything you're looking for is an element. You even have a sense of the atomic structure that's going with it and so on and so forth. But I would think that when you discover a new element, you've discovered a new phenomenon. So I'm just wondering, what is it that somehow makes the AI case different than the human case? It looks like insofar as we engage in supervised learning as humans, we still discover new phenomena.
Yeah, that's a very nice point. I mean, yeah, it does. I mean, my argument does depend, of course, on the level of novelty that you're that you're willing to accept. And as I said, in the Halcyon case, I mean, on the face of it, it does look like, you know, a really nice new discovery. And as you point out, we can think of the protein predictions also as new structures, certainly maybe new phenomena. Yeah, I mean, you can say that, but then there's still these attempts to discover something that is just so new, right? That we just don't know what it even is, and that seems to be a different class of novelty than the examples you mentioned. It's not in no way trying to downplay them, and I mean, I think these are fantastic things and important. It's just that I think there still needs to be room for this other, more radical maybe type of novelty of us trying to discover something that we basically have no clue about yet.
So here's just a packaging suggestion. Maybe the title of the talk should be, can AI start scientific revolutions?
Okay, yeah. I don't want to go too Kuhnian. I've done it too many times before, but yeah, I'll consider that.
Thanks, Karim. Joe, floor is yours.
Hi, thanks for the talk. I think some version of my question has been asked before, but I want to maybe try a slightly different reformulation. My big question is, I think you've identified a really important problem for AI, the discovery of new phenomena by AI, but I don't see why it's an in-principle problem. So the way I'm thinking about it is unsupervised learning techniques are clearly able to or capable of detecting new phenomena or patterns. So like with AlphaFold, people have used unsupervised or clustering algorithms with just amino acids and other things. And these algorithms can group them according to things like hydrophobicity or charge, right? And so it's sort of like if we didn't know about those things, it could have discovered them. And so I guess if unsupervised learning is capable of discovering new patterns or new phenomena, it seems like the important problems you're raising related to, causal relationships or shortcuts or things like that, it seems like these are very real and serious problems. But it seems like there may be some way of validation, like you recover so much of the structure that you know is there, that now the structure that isn't there seems like it must be mapping onto something. So yeah, I'm just not sure where the in-principle bite comes from. Thanks.
Yeah, thanks. That's also a very good point. So as far as I can tell, the most unsupervised learning methods do not involve DNNs to the extent that they may involve them in the physics that I've shown. So yes, of course, we have lots of algorithmic techniques that we can put to the table. But I mean, the claim was about DNNs, right? The skepticism was about DNNs. Yeah. So so maybe there are other methods. So we don't need to be skeptical about them, and we don't need to be outright skeptical about DNNs. But at least when it comes to certain questions, yes.
Thank you, Joe. We have a few more minutes for questions. Mark, come back to the.
I'm back. Let's maybe.
Don't be shy, Mark. Don't be shy.
Another thought, I mean, about the example of physics. I wonder if, one thing that AI has been good at is finding patterns in really messy data, and physics is not messy data. So maybe applying this to say economic phenomena would find us very different kinds of patterns. And in that kind of case, it might be that its ability to pick up on stuff that we don't think is causal is precisely what will be the insight. So the fact that, physics has tried this and failed seems not to be a reason to think the other sciences might not have great success with it.
Good. Thanks for the question. So there's actually some discussion of these features that DNNs pick out in the data that we don't recognize as causal, and there's been some discussion about them saying that actually, maybe that's fine. Maybe they don't need to be comprehensible to us, and they can still be super effective. And so Buckner has made this case, and Burger. But the problem is that you, in order to find these humanly inscrutable features, as they call them, you need to have some measure of the performance of the DNN, right? Because only then you can say that that the features are being identified that somehow trigger that underline or fuel the success of the network. And for that, you need a target. If you don't have a target, then you can't really train the network to sorry, I'm not sure where we're going with this thought, but yeah, I'm just worried that this dilemma is popping up again, right? So that we either need to know the target in order to identify these features that are allegedly not causal, but still fuel the success of the network, or we don't have a target, but then we can't really identify these features. That would be my worry about this. Yeah.
Good, thank you, Sam and Mark. David, yeah, please.
Great. So I had a different sort of concern. So you focus on DNNs, but of course there's many other types of neural networks. There are neural networks that sort of have these generative components to them. Recently, just last week in Neuroscience, a paper was published, a really beautiful paper where they used a neural network, I'm not sure which kind, but it was able to generate an equation to describe the tuning curves of neurons in visual cortex. There's been a long-standing issue, which is that our simplest mathematical descriptions of these tuning curves fails to explain large-scale neuronal recordings in the sense that those recordings are assessed to have a very high dimensionality, but the tuning curves that we typically use to describe responses of neurons predict lower dimensionality. And what they did is the neuroscientists threw the data basically at this neural network. The neural network was able to uncover a mathematical description. And my understanding is that, it had some sort of built-in pieces of or individual elements of possible functions, and it put the elements together in order to arrive at a new description of the tuning curves, which was actually a very principled description in the end, and the neuroscientists were able to take that description and then explain all kinds of other features of the data and so forth. Really beautiful paper. I think it came out in PNAS. My concern is that kind of scientific investigation, which based on your talk, I would think you would want to say, well, that's maybe not discovery of a new phenomenon. Maybe it's a discovery of an idea or discovery of an explanation of a known phenomenon or something like that. The problem is the considerations that you seem to level against the capacity of neural networks to discover new phenomena also seem to apply to that, because here you have a case where the neural network is given all kinds of data and it generates this mathematical description. But again, we don't know if the mathematical description is causally off, if it's just if it's hallucinating, if it's picking up on aspects of the data that don't reflect the what's actually going on to generate that data or what's going on in the phenomenon. So my concern is that by ruling out this kind of scientific discovery of phenomena, you accidentally exclude other uses of neural networks in advancing science. So I was just wondering what you might say to that case.
Okay, yeah, that sounds very interesting. The case I should look at that again. If you could maybe give me the references. Did you say PNAS?
I think it was in PNAS. Let me I'll bring it up right now.
Okay. Yeah, thanks a lot. Yeah. I mean, yeah. So that's an area where I haven't looked so much. I'm not sure that fits your description, but maybe discovery of laws, relationships. Yes, something maybe as you say yourself, maybe not quite fitting the description of phenomena. But yeah, I would have to look at that case, and it certainly sounds interesting. Yeah.
Sorry, it actually was on bioRxiv. It's not published yet, but the first author is Tilbury, Tilbury.
Okay.
Put it in the chat. Thank you. I'll put it in the chat.
Yeah.
All right. So I asked the last question. I think we're 27. We don't have very much time, and so I had very similar concerns as the ones that were expressed, but I would like to know what your views imply or suggest for formal sciences. So as you probably know now, LLMs particularly are extensively used in mathematics. So Tao has been, the UCLA mathematician has been extensively using LLM to do his mathematics. He thinks they're extremely useful. He's written quite a lot about that matter. They've developed dozens of new proofs of well-known theorems. So they've discovered new proofs. They've also discovered new theorems. Now, of course, that's as we used to say in the 1970s and 80s in AI research, it's a small world in some sense. It's that, the parameters are in some sense well defined, but there's a very clear sense of novelty here, both in terms of the proofs and in terms of, in some cases, the theorems, results that maybe the leading mathematicians or leading mathematicians find surprising, unexpected, so much that he has included that in his everyday research in mathematics. Is that different from empirical sciences? Is that the same type of concern that you might have? And if it's different, what are the relevant parameters?
Yeah. That's great. That's great. Thanks. So when I think of phenomena, I do think of phenomena as something out there in the world. And I mean, of course, if you may be a Platonist, and then you're okay with that. But yes, I mean, as I would certainly kind of bracket off mathematics as a not quite empirical science, and so then we're maybe in the realm of discovery of ideas, and there I think maybe different rules apply. Duate has this, I mean, the paper that I mentioned about discovery of ideas, that also has a math example. But yeah, I also work in a mathematics department. My colleagues are mathematicians, and there's one who, I mean, they're extremely impressed by what they can do, and some of them are being invited to Silicon Valley and being presented with the latest models, and they're just completely blown away. So yeah, I mean, I wouldn't want to downplay any of that for sure.
All right, thank you very much. I think it's time to stop. Great to have you with us, Sam, online. Hopefully soon in person here at the center. We would love to see you back here. You have a standing invitation, as you know. All right, guys.
Thank you so much for your question. That was super helpful. Thank you very much.
And thanks to the audience. So that's the last online talk of the year. We will have more talk in this series in the new year. And have a good end of the year. Ciao, Sam. Talk to you soon.
Bye-bye.
Bye.